Hi, my name is Schwarz. I'm a chemistry teacher at Gentofte HF in Denmark. Today is a small demo of an experiment with Luminol, where I would like to show the beauty of aromatic structures and organic chemistry. What we hope to do is get experiment something similar to this, but in a small beaker, and we would like to record the luminescence with a camera to see if we can find the intensity of the light as a function of time. I found a manual for 3 different experiments from ImageJ, which covers 3 different experiments, and I also have the possibility to buy a kit with Luminol, which is this one, where we already have Luminol in the powder. Then we have sodium perborate, which is an oxidizing agent, and then sodium carbonate, which will function as a base. But just to refer back to what is going to happen, we have Luminol over here. We need a strong base, and we need some oxygen, which you will need from your oxidizing agent. When we do this reaction, the final product will have the nitrogens substituted with an oxygen. We will have produced some water and some nitrogen. And if you look at the oxidation reduction reaction scheme, it looks like this. So nitrogen goes from -1 to 0, and the oxygen goes from 0 to -1. In general, you need a catalyzer. If we have hydrogen peroxide, if we add a catalyzer to this, it will decompose into water and some free oxygen molecules in the solution. The kit we have from the company is Luminol, and here's the molecular weights noted down, and here's the SAS numbers if you want to look them up. What you notice, the weight percent is 0.7 for Luminol, for sodium perborate is 12.1%, and for sodium carbonate monohydrate it's 86.2%. Sodium perborate will work as an oxidizing agent, while the sodium carbonate is a base. And here I noted down the pKb as 3.68, so if you make the reaction scheme, you'll see from this pKb that the reaction will be much forward to the right. That means that it's an effective base, which we need in this experiment. Then the oxidizing agent here is sodium perborate. When we dilute that into water, you have the sodium ions for itself, and we have this complex of perborate. I guess when we add a catalyzer and a strong base, we'll decompose into the base of boronic acid and free oxygen atoms. So that is in the same way that we have the other oxidation agent as before, hydrogen peroxide. I've analyzed the different experiments here. We've done that in class to see how much of the different components is in the different reactions. The calculation is down here. When we get from the kit, 4.7 grams, and it says that we have to dilute into 118 milliliter for ounces. If you calculate that through, the reaction is 1.57 millimolar for Luminol. For the oxidizing agent is 31.3 millimolar, and for the base it's 276.9 millimolar. So just a rough thing, there's 20 times as much oxidizing agent to Luminol and a big surplus of base. Then we need to have a catalyzer. I have decided to have a small volume to be able to do many experiments. So we want to do a 10 milliliter volume of beaker A, and the same in beaker B. Then I've decided that I want to have 1 millimolar to make it easy to calculate. And if I want that, I can calculate how much of the kit from the gram I need. 0.25 gram, which is about the minimum possible you can do on a weight. At least here. For the BKB, again 10 milliliters. The catalyzer, if you look at the free manuals, somewhere in between 1 to 5 of luminol. You can either use copper or, for example, iron. In this experiment, we will use copper. So 1 millimolar, if you calculate the mass, we get 2.49 milligram, which is way too small. So we multiplied that by 200. So that's half a gram we have to weight up, and that's okay. So I want to do a 20 times dilution and then a 10 times dilution to get the final concentration in BKB. So here we are. The copper sulfate over there. What is the mass of half a gram? I made a 200 millimolar solution here. Then a 20 times dilution, so I have 10 millimolar. And this one, let's see if I can do that better. So 210. And then the last one over here is 1 millimolar copper. Here I have 10 milliliters of water. And here I have my 20 milligrams of quarter of a gram of luminol. So that is the experiment. Now I want to record the light. So here I need to put my light, my camera, in a right position. I think I'll try this one to see how that works. So in essence, I'll just focus here. Focus, and I will lock the focus. Very good. And so now I will turn off the light, because if we have light in this experiment, then it will destroy the luminescence. So let's turn off the light. I will now first, because I can't see anything, I will start recording on my camera here. So now that's recording. I will add the powder. And then I have the catalyzer in the other beaker. Give it a little more. A little more. Just redo the recording here. Okay, I think we're ready to try. It's not totally dissolved, but this is just a test experiment. So let's do this. I start recording. Okay, here we go. And I stop the recording. there is still a luminescence quite obvious here in the laboratory. So that's working absolutely perfectly fine. It's continuously from this state, it looks like, so maybe this is the powder which is not dissolved. I will let this run for a long time. And I think this finishes the experiment. So I'll turn on the light now and then we'll destroy the rest of the luminescence. And if we go back and turn off again, there's still some luminescence. But this finished the experiment. Now I'll save the video from before and try to analyze the trajectory of the intensity versus time in another program, which I will show you.